So in this section, we are going to address the mechanical properties of polymers, like what are the tensile properties of polymers and how are they affected by the basic microstructural features of polymer. Then the processing, how hardening occurs in polymers, anisotropy as well as annealing in polymers. Then how does the elevated temperature mechanical response of polymer compare to ceramics and metal? What are the primary polymer processing methods? This graph shows the stress-strain behavior of several polymers. In some hard polymer, hard but brittle polymer, they have very here steep stress-strain curve, which indicates that they have very high Young's modulus. Then they will usually breaks after certain strain. And these are brittle polymers, so similar maybe like ceramics, but of course with lower stress. In ceramics, this can go up to several gigapascal. Then we have plastic polymer, which has an elastic region as well as plastic region, where above the yield strength, that polymer can then deform permanently. And this one shows the ultimate tensile strength. The elastic module is usually less than metal. Then finally, we have also a different kind of polymer called as elastomer, which is stretchable, very stretchable. As you can see here, it can be stretched to up to 7 strain. It means 700% of its original length, 7 times of its original length, with small amount of stress. So, for example, like rubber is very elastic, and then they are called as elastomer. Strain and deformation is larger than 1000%, even in some form of elastomer. Larger than 10 times of its original length is possible. In metals, maximum strain is usually only up to 0.1 strain or 10%. So the deformation can goes maximum 10% of the original length. What actually occurs in these different polymers? What occurs in the brittle polymers? What occurs in plastic polymers? And also in elastomer. And these are related basically with their structure, in their polymeric structure. In brittle or failure polymer, usually this is for polymer that has very high Young's modulus. It means very high strength. And as we have learned from the structure in the previous session, that this is usually occurs when the polymers are in cross-linking or otherwise in network structure, where when you have cross-linking, when that is the binding between different chains or otherwise cross network like this. So initially they are aligned, yes, but when they are near failure, this structure, some of the structure, for example, here in the cross-linking structure, becomes very close to each other and near breaking. And also, this is just before breaking, where the width is decreasing between the networks compared to the initial network case structure. Then, for plastic polymer, what occurs? So, usually the deformation occurs because of the existence of the amorphous region. Remember that polymer can have different percentage of crystallinity. Some regions are crystalline, while the other regions are amorphous. So in this point, for example, at the beginning of the elastic region of its deformation, it is due to the elongation or deformation of the semi-crystalline region or semi-crystalline part of that polymer. So when we further extend, that polymer sample or specimen, the amorphous region will elongate. Yeah. Then at this point, yeah, this is the onset of necking. This is exactly at the yield strength. At the yield strength, when it starts to have a plastic deformation, it will start to affect the crystalline regions. So the crystalline region before this stress, the crystalline region may be oriented in different direction. At this state, at this point, then they will be aligned like this, yeah, aligned and then vertically like this. Then when we extend further and further, at this point, okay, the crystalline region will slide. So remember, in metal we have what do you call it? The plane can be slipped. Yeah, the deformation can move. The deformation can move between different plane. What we call a slippage. Similarly, at polymer, crystalline region at this point can slide from one another until when it fails. Yeah, this is the failure, when the fibrillar structure of the crystal region also deform completely, and near failure until it breaks. Okay, then drawing is a process of pre-deformation. Yeah. It stretches the polymer prior to use and aligns the chain, yeah, the crystalline chain, to be in the stretching direction. The result of this is that the Young's modulus, the elastic modulus, will increase in the direction of the stretching. The tensile strength will also increase in the stretching direction. On the other hand, the elongation, percentage of elongation, or we call it as ductility, will decrease. So ductility indicates how easy we can form the material as we like. Yeah? Like also similar in metal. Polymer, when they have ductility, they can be formed. But when we do drawing to the structure, and the crystalline region will be aligned, and this will decrease the ductility. If, however, we do annealing, so similar like in metal, yeah, when we do annealing, the alignment can decrease. So they start to be misoriented towards one another again, yeah, between the crystalline region. As a result, the ductility may increase again. This is resemble that of the metals. Yeah, remember the cold work and annealing in cold working. Then in the elastomer case, on the other hand, so because most of the regions in the material in the elastomer case, they are amorphous. Yeah, in amorphous, initially the amorphous chains are kink or cross-link. When you stretch this part, the formation is more possible. They become straight. Yeah, they form. For example, here we deform in a vertical direction. The chains become straight. However, they are still cross-linked to each other, so they do not break. So that is why with elastomer, like rubber, we can stretch them to many percent of their many times of their initial length. Compare this to the response of the other polymer in brittle response, yeah, with the hard polymer in this brown response. The material, the crystallinity is, crystalline regions are aligned and cross-linked or cross-linked and network polymer. In this plastic polymer, it happens because they are semi-crystalline polymer. Some parts are crystalline, some other parts are amorphous. And in elastomer, they are completely amorphous. So we also know thermoplastic polymer and thermoset polymer. In thermoplastic polymer, they have little cross-linking, and therefore they are ductile. They are easy to form. They're easy to deform, to make different kind of various shape. Yeah. So most of the plastic that we saw, that we see in daily life and we use, those plastic bottle, plate, spoon, etc. They are made from thermoplastics material. This plastic also soften with heating. So some examples are polyethylene, polypropylene, polycarbonate, and polystyrene. And the second type of polymer, the Thermoset polymer, they have large cross-linking with up to 10 to 50% of the mass. Therefore, structurally they become mechanically they become hard and brittle, and even when you heat, they do not soften easily. An example is vulcanized rubber, epoxies, polyester resin used to glue or to attach between parts, and also phenolic resin. So this is the similar to phase diagram in metal, but this is temperature to molecular weight. In tough plastic, usually they have very high molecular weight because of the large cross-linking. In viscose fluid or crystalline mobile liquid, here with when it is at high temperature, even and the molecular weight is small. Now, this graph shows the relationship between temperature and strain rate in thermoplastic material. When the temperature is decreased, for example, here from 60 to 40 to 20 to 4 degrees, the Young's modulus will increase. The tensile strength will also increase. They become more brittle because the ductility decreases. The percent elongation decreases, so they become brittle. At 4 degrees Celsius, for example, this is for PMMA, acrylic or plexiglass, very hard, it becomes very hard material. When you increase the temperature, however, then they become softer material with a lower Young's modulus and even more ductile. While by increasing the strain rate, you also by doing stretching, by what you call like similar like drawing in the previous slide, it will have the same effects as decreasing the temperature. So this is the polymerization process. We have actually touched a little bit this topic in the previous session. As we mentioned that at the beginning, it starts with an initiation process. So a radical that is introduced to the raw material of the polymer will make that monomer becomes radicalized. Okay, because of this bond, and will breaks the unsaturated bonding between the carbon atoms to bind to that radical, and then create a new radical, a larger radical. And this larger radical can then propagate throughout the whole material to make larger or longer chain of polymer. Finally, when two radicals like this meet to each other, the dangling bond will bind and they become larger molecule with the two ends are connected to the R functional group. Okay, and this termination can be done either through like this disproportionation process, or through combination process. In disproportionation process, here we see that one of the radical does not have the same molecule structure with as the other. In combination, it does the same radical. They combine into a single long chain, but then becomes deradicalized. So they don't have any more dangling bond that can attack other other monomer molecule within that material. And then the condensation is another condensation polymerization, one process of polymerization, where we have here the edge of the one of the monomer binds to the OH functional group, the hydroxyl functional group. Then will be released as water, while the two monomers will bind to form a new polymer. So this is the formation of nylon 6,6 from hexamethylene binding to adipic acid. Polymer additive is material that can be used to improve the mechanical properties of the polymer, or to make the polymer more processable or more durable. For example, the additive can function as filler, where it add and added to improve the tensile strength of the polymer, or abrasion resistance, or toughness, or otherwise decrease the cost, like carbon black and silica gel. The wood flour, the glass can be also added to polymer to add strength, limestone, talc, etc. Plasticizer is another type of additive that is used to reduce the glass transition temperature of the polymer, so that then it can be more ductile and be formed or to differentiate. For example, it is commonly used to PVC, polyvinyl polyvinyl chlorine, yeah, because PVC is known as a brittle material, very hard plastic. How to form it, for example, how to make it into a cylindrical shape as tubing or pipe. And this is impossible if we don't add plasticizer. Then stabilizer, where we can make the polymer to protect the as UV protectant, so that the polymer does not degrade easily upon radiation by UV radiation, or as antioxidant. Lubricants, polymer additive is added to allow easier processing of the polymer. So then it will slide through the dyes easier. Some example like sodium stearate. You can add also colorants additive in the form of dyes or pigments to color the polymer. Flame retardants to prevent the polymers from burning. How to process the plastics? How to process the polymers in thermoplastic polymer, since it is quite processable using heat. Yeah. It can be reversibly cooled and reheated. Yeah. The heat will make it softened, so that then we can shape, we can form the material to shape as we like, yeah, to be like a cup, to be a bucket or whatever, and then we can cool it down. An example that of polymers that can be used, that can be processed like this, are polyethylene, polypropylene, and polystyrene. Thermoset polymers, on the other hand, when heated, it will form a network, degrades, and not melts when heated. So it just degrades. It doesn't melt, because when melting, it means that the structure actually remain intact. Only the secondary structure is it's gone, or starting to be gone. That's what happened when a material melts. But with thermoset, it just degrades. So it means the polymer degrades and becomes the basic monomer again. So to process thermoset polymer, what we use is usually by molding the pre-polymer to allow for further reaction. For example, urethane and epoxy. Polyurethane is used many times to build human phantom, yeah, a model of human flesh. Yeah, human phantom. As well as polyurethane can be used also for many biomedical devices like tubing, pipe, etc. Epoxy is used for glue, usually, yeah, or gluing or adhesive epoxy to attach or to harden structure. Molding is done by like this, compression and transfer molding, where the thermoset or thermoplastic material is being put inside a mold case and being heated or cooled down. yeah, between these two shape. Yeah, this is the mold plunger that will goes down and then form the shape of the plastic. Yeah, and this is moved using hydraulic plunger, more similar like a tensile testing machine. In injection molding, this the polymer is fed through here, okay, and it will be exerted to a hydraulic pressure and also heated at the same time. And that molten material, molten polymer, will be injected through this nozzle into the cavity on the other side. This is used for thermoplastic as well as some of the thermoset. Extrusion is similar, but it is the molten, yeah, the plastic pellets here are being fed through this hopper and then being transported using this turning screw. And along this transportation, it is being heated so to melt and then finally being shaped in the shaping die and extruded through one hole to form into tubing and pipes or sheets and film or other structural parts. So we have mentioned about the characteristics and properties of elastomers, yeah, which can deform or extend many times of its initial length. And one of the example is rubber. So an example of the rubber has cross-linking in its structure. Examples are natural rubber as well as synthetic rubber. Synthetic rubber like SPR, styrene butadiene rubber, it contains butadiene group as well as styrene group, and then makes a long chain. Silicone rubber, yeah, this is also quite familiar for breast implant as well as for many other biomedical device. Yeah, it has a silicon atom in its monomer connected to two methyl functional group and oxygen. And when the length ratio to the ratio of length to diameter is above 100, so it means it's going to be considerably very long compared to its diameter. We call the polymer as fiber. As fiber. Usually in textile, the polymers are in the shape of fibers. Because, it must have high tensile strength and usually high crystallinity as well as highly polar. Fibers can be formed by spinning. So I think this is really what you, Ezra and your batch are interested, right? To develop biodegradable fibers as medical sutures. It can be formed by spinning, and spinning can be electrospinning and many different types of spinning. Yeah, the polymer is extruded through a spinneret. For example, platinum plate with 1,000 holes of for nylon. In rayon example, this is a kind of textile which has also cotton as its ingredients mixed with other fibers. Dissolved in solvent, then pumped through die head to make fibers. The fibers are drawn and leads to highly aligned chains fibrillar structure. Polymers can be also coated thin film on surface like paint and varnish. This is used to protect item, also to improve appearance, also can be used as electrical insulation. Polymer can be used type as adhesive to produce bonds between two adherents, bonded by secondary bonding or mechanical bonding. Polymer can be made also as films by using blown film extrusion process, or can be made as foams like gas bubbles in plastic. This is the blown film extrusion to make film of polymer. Yeah, this is the polymer being heated, become molten. In liquid state, it is extruded through via this extruded and being formed in this tubing die. Okay, and then air is blown here so that then a cavity will form. Yeah, this is in the side. Cavity will form, and the surrounding sheet of polymer become is goes through these guide rolls and pitch rolls to become film, and this later becomes plastic bags like we have, yeah, or plastic film or plastic sheet made from this kind of processing, blown film extrusion. So in biomedical application, we use a lot of advanced polymers. Is for example, ultra high molecular weight polyethylene. So polyethylene but has long chain, yeah, which makes it to be very heavy, yeah, or having a high molecular weight. And the molecular weight can goes up to 4 million gram per mole per mole. It has excellent properties for variety of application. For among others, bulletproof vest, golf ball cover as hip joints. This example, hip joints. It is used in combination with metal as well as here another metal which is coated with ceramics, yeah, to make it more wear resistant. Yeah. So this is hip replacement, total hip replacement. This one I think titanium or stainless steel 316. So a summary, then the general drawback of polymer are that, among others, the Young's modulus, the yield strength, the temperature, the melting temperature, the coefficient here are generally small. Therefore, the deformation is often temperature and time dependent. Usually, then polymers will benefit from composite reinforcement. If we want to use polymers in real application, usually they are mixed with other material to make a composite. Thermoplastic, they have like polyethylene, polystyrene, polypropylene, polycarbonate. They have smaller Young's modulus, smaller yield strength, uh, and temperature of application. They have, but although they are more ductile, they could easily be formed and recycled. Okay. Elastomers rubber have large reversible strain. You can extend the multiple times of its initial length, and then it can still come back to its original shape or original length. Thermosets material are harder polymers like epoxy or polyester. They have larger Young's modulus, higher Young's yield strength and temperature of application, with smaller Kc. Okay, are there any questions regarding structure and properties as well as processing of polymers?
Sir, tadi KC itu apa?
A good question. Let me check. I'm not that familiar also with Kc here. Seldom use. I will check later. Yeah, I will check later. Let me check later in the textbook also. Any other questions? I will answer you later. Any other questions? Okay, if not, then please first fill in the